Today we're going to continue section 8.1 and look at some other ideas that have to do with right triangle trig. To start off with, we're going to look at the idea of cofunctions. So here we have our right triangle with the right angle at C, opposite of side C, the angles A and B, and the sides A and B. If we look at this triangle, the sine of angle A, opposite over hypotenuse, would be A over C. And the cosine of angle A, adjacent over hypotenuse, would be B over C. If we look at the other angle, angle B, its sine, opposite over hypotenuse, is B over C, and its cosine is A over C, adjacent over hypotenuse. So if we look at these values, what we see is that the sine of A gives us the same thing as the cosine of B, and the cosine of A gives us the same as the sine of B. This is actually why this is called sine and cosine. The co stands for cofunctions. And there's a rule that says cofunctions of complementary angles are equal. Angle A and angle B have to be complementary because they are the acute angles in the right triangle. They have to add up to 90 degrees. So when we take the cofunctions of those complementaries, they are equal. The sine of one angle is equal to the cosine of its complementary angle. The cosine of an angle is equal to the sine of its complement. Well, there's actually three pairs of cofunctions, and again, we can see why they are named this way. The sine of angle A is always equal to the cosine of the complement of that angle, which in this triangle would be angle B. The cosecant of A is equal to the secant of the complementary angle. And the tangent of A is equal to the cotangent of the complementary angle. And again, sine and cosine, secant and cosecant, tangent and cotangent, the co part of the name comes from cofunctions. The next couple examples are from SAT and PSAT problems, where if you know this cofunction relationship, you can solve the problem without any real calculations. Here, we're told that in this triangle, the sine of x is 0.6, opposite over hypotenuse is 0.6. And the question asks, what is the cosine of y? If we look at this, angle x and angle y are complementary angles. And the rule says that cofunctions, sine and cosine, of complementary angles are equal. This was a gridded problem, and the answer is 0.6. You could also set up this problem by saying sine is 0.6, that's 6/10, and then you could find this cosine of y by doing adjacent over hypotenuse and again get the 0.6. But if you know the cofunction rule, there's no work required. Here's another example where you were told that the angles shown were Q and the sine of A equals the cosine of B. Here we have cofunctions that are equal to each other, so that means that the angles must be complements. So in this problem, recognizing that those angles have to be complements, you can write an equation to solve for K. You have 10K minus 35 equals 90. Add the 35 over, and you get K is 12.5, which was option C. So this is something that we've seen show up over and over within some SAT problems. Just a heads up that it may show up in those tests. The other thing we're going to add in today are some application problems, and you did a lot of these in geometry when you did right triangle trig. When a lot of these problems have to do with angle of elevation and angle of depression. Angle of elevation is the angle above the horizontal. So this occurs in problems where you have an observer on the ground looking up at an object. So the angle of elevation is the angle from the horizontal, which is either at ground level or at their eye level. And you're looking at how do they tip their head up to have a direct line at the object. That's the angle above the horizontal. Angle of depression is the angle below the horizontal. So here you have your observer up in the hot air balloon. The horizontal is straight across from their height. Angle of depression is the angle coming down from there to their sight line. And so this would occur in any problem where you have someone looking down at an object. One note here, if you had a person at the ground looking back up at this observer, their angle of elevation would be here. And in geometry, we know that these are alternate interior angles and they would be equal to each other. So in these problems, the angle of depression of the person looking down is always equal to the angle of elevation of the person looking back up at them. Here's a simple example using this type of problem. We have a ship offshore from a vertical cliff that is known to be 100 feet in height. Here's my cliff, it's 100 feet tall. And here's the water. We have a ship that's offshore, takes a sighting of the top of the cliff. The angle of elevation is found to be 25 degrees. And don't overcomplicate these. We're going to assume that we're looking at a straight line from the boat up to the top of the cliff. Angle of elevation is the angle from the horizontal up. Here's my 25 degrees. We have to assume vertical, horizontal, or perpendicular. And we want to find out how far offshore the person is. We want to find this horizontal length. We have the two legs that are the important sides, so we're going to use tangent of the angle equals opposite over adjacent. I'm going to solve for x, which would be 100 divided by tangent 25. And then when I put that in my calculator, I get about 214.45 feet. And again, get in the habit of rounding to the nearest hundredth in these trig problems. And make sure that you are still in degree mode. Put units on any application problems. One other type of problem you'll see today is a bearing problem. Bearing is used in navigation and surveying. The definition of bearing is the bearing from a point O to a point P equals the acute angle between the ray OP and the vertical line through O, the north-south line. So for example, if P is over here, we need to draw in the line, the ray from O to P. Let's do this. The bearing of point P is the acute angle between the ray OP and the vertical line through O. So this point P is north of O, and we would need to know this angle. So for example, say that this is 26 degrees. The way that I would write the bearing of point P is to say that it is to the north and 26 degrees to the west. You always give north or south first, and then how many degrees off the north-south line, and then whether it is to the west or the east. Here's an example. A ship leaves the port of Miami with a bearing of south 80 degrees east and a speed of 15 knots. After 1 hour, the ship turns 90 degrees toward the south. After 2 hours maintaining the same speed, what is the bearing of the ship from the port? So we need to set up this problem by drawing ourselves some axes and looking at where this ship goes. So this ship starts out with a bearing of south 80 degrees east. So here's south and east. We're going to go south 80 degrees to the east, which is over here, right? South and east. The 80 degrees is this angle, which means it's 20 degrees out here. Then, if the ship, that goes for 1 hour. And with this problem, you could either use distances or times since we're going the same speed the whole time. Let's label this as 1 hour. Then you're going to turn through an angle of 90 degrees. And turn and go 90 degrees toward the south. So that's going to come this way. And the ship is going to continue in that direction for 2 hours. So we would label this side, make this a little bit longer so it's more to scale. We would label this side as having a length of 2, and this is a 90-degree turn. What we want to do is find the bearing of the ship from port at this time. So we need to figure out where this line is. And the bearing will involve the angle here. But what we can find is the angle inside of the triangle. So let's call this angle theta. I can say tangent of theta equals opposite over adjacent. So theta is the inverse tangent of 2 over 1. Inverse tangent of 2, that angle is 63.43 degrees, the angle inside this triangle. Now, it becomes a little bit of a puzzle at this point. We have to figure out what the missing angle here is. In this case, we knew we had 20 degrees above, 63.43 inside the triangle. So that angle that's left near the south line is going to be 90 minus 63.43 minus 20. That angle is going to be 16.57 degrees. The one thing you have to be careful of in these problems is to check if your angle has passed over the north-south line. In this case, we're still in the same quadrant. So we want to give our final bearing from the port. We're in the southeast quadrant, so it is south 16.57 degrees to the east. And that is bearing.